A very warm good afternoon to distinguished guests and dear colleagues. Welcome to 8th CSIR-CDRI Nobel Symposium. I am Sara Fatima, your host for today's event. The Nobel Prizes was first awarded in 1901 through the vision of Swedish chemist and inventor Alfred Nobel, whose 1895 will dedicated his fortune for honoring the achievements that benefited humanity in the field of physics, chemistry, medicine, literature, and peace. Later, the category of economics was also added. Since then, Nobel Prizes have recognized the extraordinary contribution in science, culture, and global harmony. We here at CSIR CDRI commemorate the legacy of Alfred Nobel by celebrating those whose work continues to advance and inspire the world. Initiated by our former director, Dr. Tapas Kundu, the CSIR CDRI Nobel Symposium remains a key fixture under the guidance of our present director, Dr. Radharang Rajan. Before moving forward, I'd like to invite our respected director to the podium. May I request our volunteers to please present a bouquet to ma'am. Remain on stage for your welcome address.
Thank you. Good afternoon to everyone here, faculty, staff, and my dear students. Welcome to the 8th edition of the CDRI Nobel Symposium. Every year we convene to hear about the scientific journeys of those scientists who, through the body of research that they have done, win the prizes for chemistry and physiology or medicine. This symposium is really unique because it is run by the students, and it gives us an opportunity to learn about groundbreaking work that has played out over decades and is then recognized for its foundational value. So even if we don't work in the specific areas that the student presentations cover when they talk about the prize-winning work, it is still a great opportunity for all of us to learn. And of course, the fact that the students are teachers here is another really fabulous angle about this symposium. So I'm truly heartened. The participation of the students year after year is commendable. We usually do this at the end of the year. So this was supposed to be in December 2025, but because our calendar was so full, it rolled over into 2026. So actually this year we'll end up doing 2 Nobel symposiums. As Sara Fatima mentioned, the Nobel Prizes are endowed by the money left behind by Alfred Nobel. Most of you know that his work as a chemist was in developing dynamite. And dynamite became the means through which violence and wars were won, causing great grief to Alfred Nobel that his scientific discoveries had been turned into an agency of war against humanity. So when he died, in his will, he wrote that a foundation was to be created, and he donated 35 million Swedish kroner, which is about $265 million. And he said it was to be given to those who have selflessly worked for society and have conferred the greatest benefit on mankind. And as she mentioned, the Nobel Foundation laid down 5 categories. P economics was added in 1968, and the first Nobel Prize was awarded in 1901. So today we'll hear about the scientific journeys of Nobel laureates who won the prizes in chemistry and physiology in 2025. The prize for chemistry was won by Drs. Susumu Kitagawa, Richard Robson, and Omar Yagi. Their research on metal organic frameworks has had tremendous impact, seeding an entire new field in material science and resulting in many applications. Metal organic frameworks are crystalline materials built from metal ions linked by organic molecules, forming rigid structures with enormous internal surface area through which liquids and gases can flow. The chair of the Nobel Committee compared metal organic frameworks to rooms in a hotel so that guest molecules can enter and also exit from the same material. He said, a small amount of such material can be almost like Hermione's handbag in Harry Potter. It can store huge amounts of gas in a tiny volume. So this is to give you the context of why this was considered so foundational and prize-worthy. The prize for physiology or medicine went to doctors Mary Brunkow, Fred Ramstel, and Shimon Sakaguchi for their work on regulatory T cells. These are cells that keep the immune system in check. Once considered a biological curiosity, we now know that these cells prevent the immune system from turning on itself. So they're a very key part of tuning the immune system. And this work has led to very innovative therapies which are still in development for autoimmune diseases, type 1 diabetes, cancer, and others. So today's presentations will be made by Ipsha Shruti, Aniza Noor, Chainika Chatterjee, Adi Shri Yadav, Sakshi Yadav, and Priya Saha. And the event is being moderated by Sara Fatima. Students have put in a huge amount of effort to make the presentations today. This stands as one of the unique learning platforms that students themselves sign up for, and they do much of the work on their own. Of course, they're guided by mentors, but it is scientific curiosity and a willingness or a desire to learn more that really drives them to participate in these symposiums. So kudos to all of them. They have taken time out of their daily routine to study a completely new area, and I really want to congratulate them for their sincere efforts. Of course, this would not be possible without the efforts of our two mentors, Dr. Neeraj Jain and Dr. Tejinder Thakur. Thank you so much for taking the time to mentor the students, for helping them put together high-quality presentations, for your patience, hard work, and for your commitment to students learning and becoming the next generation of scientists. Thank you so much for your efforts. And to all of you here in the audience, I'm very glad to see you here. I will say that I would really like for all of you to think about being on time to events like this. Every minute counts. Time is money. Time is everything. And so the difference between being here at 2:30 and 2:40 is leaving from wherever you last were 10 minutes sooner. So think about it. Let's try and be more on time in the future. Nevertheless, not to take the shine away from today's symposium, I'm now going to hand it back to Sara Fatima for conducting the proceedings. And thank you very much for being present and for encouraging the students in their efforts. Thank you.
Thank you so much, ma'am. We will now begin the session 1, the Nobel Prize in Chemistry. This year's coveted Nobel Prize in Chemistry was jointly awarded to Susumu Kitagawa, Kyoto University, Richard Robson, University of Melbourne, and Omar M. Yagi, University of California, for the development of metal organic frameworks. On 8th of October 2025, the Royal Swedish Academy of Sciences announces the Nobel Prize in Chemistry awarded for the development of metal organic frameworks. These are the structures that are assembled with metal ions and organic linkers having large cavities. After the groundbreaking discovery of the laureates, the field has rapidly expanded, with thousands of MOFs being discovered, tailored according to the applications, ranging from drug delivery, gas storage, carbon capture, and atmospheric water harvesting. Before moving forward, let's have a look at the award ceremony.
Of metal organic frameworks. This is a truly great achievement for the benefit of humankind. On behalf of the Royal Swedish Academy of Sciences, I wish to convey to you our warmest congratulations. May I now ask you to step forward and receive your Nobel Prizes from the hands of His Majesty the King.
Professor Susumu Kitagawa, born in Kyoto, Japan, where he still works at the Kyoto University. Professor Richard Robson, born in 1937 in Glasgow, UK, has travelled much farther and built his career at the University of Melbourne, Australia. University of California can claim the fame of several Nobel Prizes this year. This one goes to Professor Omar Yaghi, born in Amman in Jordan. We move on to the
So, Richard Dobson was the first to conceptualize a process and demonstrated the utility and applications of such materials. He asked the question, can we make materials like the giant version of diamond? To walk us through the pioneering work of Richard Dobson, may I request our first speaker, Ms. Ipsha Shruti, to please come up on the stage.
Thank you, Sarah, for the nice introduction. So, good afternoon, everyone. It is my honor to speak at CSIR-CDRI Nobel Symposium. So, today I would like to take you on a conceptual journey, not through a material science only, but through a shift in scientific thinking, a shift from molecule to material, from bond to network, and from matter to designed space, because these all are the fundamental units from which we can synthesize metal organic framework. So before understanding why MOF is chosen for a Nobel and why it is so powerful, let's have a quick and basic entities behind MOF, that is called dimensionality, from which we can synthesize from zero dimensional to three dimensional infinite framework. So let's talk about a very basic element in chemistry, that is carbon. And beauty of carbon is that same element with same type of composition can produce different materials such as fullerene. It is a finite case, and that's why this is zero dimensional. And moving further, if carbon extended in one dimension only, it forms a carbon nanotube. Similarly, in graphene sheet, it is infinitely extended in two dimension, and finally we have a diamond structure, and we all know that it is infinitely extended in all three direction and making it very beautiful and stable structure. Now what's the catch here? Elements are similar, Compositions are same, but the difference is the direction of growth. So, taking inspiration from these, few researchers have thought about if a nature given us this much a stable framework with us, then can't we make these in lab? And this is thought by Richard Robson. So how he got his this idea or curiosity and how he started working on making moths. First, I would like to show you his educational background, that he has done his BA and DPhil in 1959 and in 1962 from Oxford University, followed by two postdoctoral from Stanford University. Then he joined University of Melbourne, where he has done lot of research on moth and synthesized numerous framework and got a Nobel Prize. And he retired as an emeritus professor in 2004. So next slide shows how molecules shift from organic polymers to a metal organic framework. As I mentioned, many researchers have explored to synthesize extended frameworks, which include organic polymer. The organic polymer has connectivity, but the limitation is that it lacks long range order. It means the atoms and elements are not periodically arranged, and these are limitations. And MOF offers solution to this limitation. In case of MOF, metal, if we talk about the basic definition of MOF, it is made up of metal ion cluster and linkers, where metal ion act as a node and organic linker act as a spacer and work on a node spacer strategy. So here, not only single metal we normally use, it could be a metal cluster such as trihedron, tetrahedron, polyhedron. Why? Because it decides the direction of growth. It is giving the directionality. And organic, and we can have a different functionality of organic linker with different lengths, because it is going to decide the length between metal ions, and from which we can tune the pore shape and size of whole framework. Now coming back to Richard Robson's story, he was doing his normal routine lecture back in 1974, and he was taking class of grad second year student, and he was teaching that ball stick model. And after visualizing this model, he got an idea. What if it's not idea, or it's a curiosity? What if we replace this ball and stick from the element present in our lab? Can we make such a stable shape? Can we make that hollow space in between them, or we can use for a different application? And that curiosity led him to report the first stable framework, and he got his inspiration from rutile topology, because he said the solution is topology net. And we all know that rutile is naturally occurring mineral, and it is made up of titanium oxide. And because he thought about of replacing ball and stick model, so here he replaced titanium with zinc, and the bond between titanium and oxygen with tricyanomethanide, and got a first stable framework. But now he is more interested into designing space. So that's why simultaneously he started analyzing the architectural framework diamond. And we all know that diamond is purely made up of carbon, and carbon is connected with other 4 carbon. So he replaced this carbon with copper ion, and the bond between carbon with trinitrile, and got a first extended framework which has cavity. Now he didn't stop here. After 4 years, he again got inspired from a natural mineral, that is platinum sulfide topology net, and he mimicked exactly same topology by replacing platinum sulfide bond with cyanide bond, and got a first porous layered framework. Then moving further, because I said he is more interested in designing space porous, he replaced that cyanide bond with a porphyrin, because porphyrin is have larger length than cyanide, and he got the first framework with a large pore size. Now in 1996, he again got inspired from one natural occurring minerals, that is boracite, and it has a 3-4 topology net, because it is made up of boron, and boron had 3 bond and 4 bond itself. So he exactly mimicked the same 3D like structure, which where he replaced boron with copper and linker with TPT, and report that we can make a stable framework, cavity included framework, layered framework, bigger size pore included framework, and 3D cage structure framework also. Now, after 2 years, in 1998, he intentionally built a first chiral 3 connected MOF like structure, and from where this is all a benchmark revolutionary MOF given by him. And after this chiral MOF, all closed gates are open of like selective reaction, asymmetric synthesis like that. So now anybody can have a question like, what's so fashionable about this mimicking structure, replacing natural occurring minerals with elements in chemistry? What is the use of this? So basic use of MOF, if we see how MOF works, it's like a building which we used to live in it. It is made up of roof, floor and wall, but we are using the space. That space is used for a numerous applications that will be discussed by other speakers also, but two applications I will discuss here. First one is drug delivery and the second is catalytic application. So this slide shows how MOF is used in a drug delivery. So as I said, MOF has a designed space, and because of its crystalline and porous nature, it can encapsulate drug molecule, protect it, carries it, and deliver at right place in right time, and very importantly in a controlled manner. That is very important. So this is the first example, or here we can say that MOF is not act as a chemical structure, it is act as a container. This is the first example of MOF for drug delivery by delivering ibuprofen, which we know it is a widely used anti-inflammatory drug. So this is via CD-MOF. This CD-MOF is made up of cyclodextrin and which is already a biocompatible. So researchers have loaded ibuprofen in a cavity of CD-MOF5 and release in a controlled manner rather than all at once time, and they reported CD-MOF have enhanced the bioavailability of ibuprofen. Now next slide shows the timeline of MOF, how it moved from simple chemical to a biomedical application. As I mentioned, in 1990 it is already introduced. So in early 2000 it is used for a drug delivery such as ibuprofen and other small molecules and enzyme encapsulation and imaging. By 2014 and 16 onwards, it is used for delivering biomolecules such as siRNA, proteins, virus, and even vaccines, just to understand the cellular uptake. From 2017 onwards, due to a structural engineering which enhance the biocompatibility of MOF, it leads to a first clinical trial of MOF using CRISPR and Cas9 and other many more MOF, that is RIMO 401 and 301, which is used mainly in tumor therapy. Now nowadays many more MOF has been used for miRNA delivery, for scalability, for safe formulation and other viral application. So this slide shows the transition, how a simple lab material started and end up to a clinically proven platform. Now we move toward the other application part, that is catalytic application. This schematic diagram shows how MOF is used in a catalysis. So here reactants diffuses through the MOF at active sites, and that sites could be a MOF node and functionalized linker and a defective sites, and the space between these MOF enable encapsulation of active species that leads to happening a smooth reaction where internal framework can pre-activate the substrate, which enable cooperative analysis, and this whole confined environment can produce a selective products. Now I would like to show you a few examples which are mostly used in labs for catalytic application. So this MOF is given by a Mukuto Fujita. It is made up of cadmium 4,4 bipyridine, and he report that the square space in between them can trap that molecules which normally not possible in solution phase. So now second MOF, that is CPF5 manganese by Bell and Martin, it is made up of manganese, and he said that because of manganese it has a skeleton body and it stops the clumping of elements and that enhance the catalytic activity. Nowadays many more MOF has been introduced already, and people are working on it, like a UIO 65, MOF 5, MIL 100, and for a numerous application. So before concluding my talk, I would like to show you a brief history of metal organic framework. As I mentioned, in 1919, Hoskin and Robson proposed scaffold like diamond, followed by Yagi, who publishes first hydrothermal method in 1995. Then Kitagawa publishes first zinc-based framework which can store gases. And in 1999, Yagi publishes first revolutionary MOF, that is MOF 5, which is used for numerous applications, which will be discussed by other speakers. Until now, 2025, we have almost 128,000 MOF registered in our Cambridge structural database. So, what's the message of this talk? It's not by me, it's by Richard Robson, that the objective is not simply to make new compounds but to understand how connectivity gives rise to structure. Thank you.
Thank you so much, Ipsha. Richard Robson provided the blueprint of the structures inspired from nature. His structure was fragile and the framework would collapse once the guest molecule was removed. Kitagawa turned Robson's fragile scaffold into stable and flexible MOFs. He asked the question, can we make those diamond like structures stable enough to hold the gases? His work led to a stable morph. He showed us that some morphs could breathe, expanding to take in the molecules and contracting to release them. Ms. Aniza Noor will be discussing about the work of Susumu Kitagawa and what led to his Nobel Prize achievement.
Good afternoon, everyone. Thank you, Sarah, for introducing me and inviting me over here. Today, I will be taking you through a journey in chemistry, a journey of how crystals, once thought to be rigid and lifeless, learn to breathe. This is the story of Susumu Kitagawa's soft porous MOF crystals and how they reshaped our understanding of solids. We begin with where the field stood before Kitagawa. Richard Robson's coordination frameworks were beautifully geometric. They were precise, ordered, and almost architectural. But they were silent structures. They had no permanent porosity, no ability to breathe, and also no flexibility to respond. Kitagawa enters here with a radically different imagination. He asks some questions. What if a porosity could be alive? What if a solid could transform? And those questions changed everything. Before we enter the science, I want to briefly share the academic journey of Professor Susumu Kitagawa. Professor did his bachelor's and master's from Kyoto University in coordination chemistry. He further pursued his PhD in the same university on metal ligand frameworks and gas sorption. Later, he joined the same university as a faculty and is currently holding the director position at Institute for Integrated Cell Material Sciences. Returning back as faculty gave him the freedom to explore his unconventional ideas, the curiosity that eventually sparked the concept of breathing crystals. Let me quickly walk you through Kitagawa's 20-year journey because his discovery didn't happen overnight. In the year 1983, he started working on very basic coordination polymers. Nothing porous, nothing flexible, just basic structures. By 1992, he first observed hints of pores inside structures, but those structures were still too unstable to be useful. Then came the real turning point in the year 1997, where he created first stable porous framework with open channels that can hold and release gases without collapsing. Between 2000 and 2003, he completely shifted in studying flexibility, showing how some of the MOFs can breathe, react, and even adapt. And finally, by the year 2005, this idea matured into a new class of solids called as soft porous MOF crystals, where porosity is dynamic rather than rigid. Moving into the beginning of his journey, what we call the seeds of living porosity. One of the most important turning points in his journey came when he started working on very simple copper chemistry. While exploring copper coordination polymers, his group found accidentally pores and structures inside the molecules that were loosely holding solvent molecules inside them. And finally, by 1997, he succeeded in creating a stable porous framework channels that can actually hold and release gases without collapsing. That breakthrough marks the true birth of what we call soft porous MOF crystals. Now let's see how a soft porous MOF crystals actually move, which is the heart of Kitagawa's contribution. Traditionally, we think solids are rigid and lifeless. Their structure couldn't move, but Kitagawa challenged that idea. The framework you see in this slide shows, the image you see in this slide shows the framework that can subtly expand, react, and even contract. So instead of behaving like hard and static crystals, these materials respond when molecules enters and leaves them. So this is why we call them soft. Not because they are physically soft to touch, but because their internal structure is flexible. And this flexibility creates a new category of solids that can adapt, react, and respond, something no one believed earlier. So this single concept, dynamic porosity, opened the door to all the functions we will see in the next slide. Now let me take you inside a breathing crystal. To understand Kitagawa's idea, we will look into the evolution of MOF across 3 generations. The first generation MOFs were rigid. They had fixed pores and fixed spaces, and the framework did not respond to external stimulus and collapsed. While the second generation MOF improved this by allowing certain gas molecules to enter them. These structures can absorb different gases, but still the structure did not change. So these were physisorption based system, that is, gases go in and out, but still the crystal did not change. Then came the real turning point, which was third generation MOF that came from Kitagawa's idea. Here, pores are not passive. They can adapt, react, contract, and even respond like soft materials. External triggers like light, heat, pressure, and even guest molecule can change the structure on and off like a switch. So from rigid solids to gas-absorbing frameworks to fully responsive breathing crystals, Kitagawa transformed MOFs into living materials. Now let's see how a soft porous crystal actually moves. On the image, you see the guest molecule enter the pore. When that happens, the linkers inside them slide, rotate, and even bend, as shown in the illustration. This movement opens pathway, a process what we call gate opening behavior. Sometimes a whole pore can move, as shown in this picture. It can expand or contract, and this is the breathing step. Now, what makes this special is that even while moving, the crystal does not lose its order. The structure stays crystalline during this entire transition. So, in simple words, these images show how a guest molecule trigger motion and how these molecules respond to them by changing their structure without breaking. Now let's see how a crystal actually behaves when a gas molecule enters it. These graphs here show methanol adsorption inside a flexible morph. You can see as the methanol starts entering the pore, the structure suddenly expands. This is the breathing step. At low pressure, the framework stays closed, so only a little gas enters it. But once a threshold is reached, the pore opens up and the morph takes in a large amount of methanol at once. This sharp jump is what we call gate opening behavior, and it shows how soft porous morph crystals can selectively adsorb different gases depending upon the size and interaction. And this is what makes these useful for smart separation and controlled uptake. So until now, we saw how these crystals adsorb different gases. But Kitagawa's idea go beyond just hold molecules. It can, you can see the framework he showed, that framework actually moves when a gas molecule enters. As you can see in these animation, the pores open wider when a molecule enters and then closes back when it leaves. This breathing allows a crystal to do real functions and just not hold molecules. It can sense materials, separate them more selectively, and even change their properties like magnetism. So this slide introduces a key message, a solid that responds like a living system. And this comes truly from their breathing and responsive nature. Now this slide shows two unique functions which only came from Kitagawa's morph crystals. On the image shows here the polymerization inside a flexible morph. Because these pores are flexible, they can act like tiny reaction chambers. Inside them, small liquid molecules can join and grow into polymers in a controlled way. On the right, the image shows the magnetic switching. When a framework breathes, that is, opens and closes, it changes its electronic environment as well. This breathing switches a magnet on and off. Both of these functions were not possible in rigid morph. They only happen when Kitagawa made these crystals flexible. Now, after seeing the breathing behavior and all the functions, this slide answers a simple question. Why did all of this matter? Kitagawa changed how we think about solids. He showed that solids can shift shapes, their pores can open, close, and even rotate. He also showed the responsive and adaptive behavior of the crystals. Guest molecules trigger real structural motion. Porosity becomes alive, that is, change with the surroundings. This breathing behavior created new functions. Flexibility enabled selective separations, sensing and switching. Reaction inside pores, that is, polymerizations, become possible. Finally, this changed the entire direction of framework chemistry. From just making rigid solids to designing materials that can breathe and flex. And that is why Kitagawa's idea is considered revolutionary. Now, soft porous crystals are not only about breathing. They give us real functions as well. The slide here shows how they can be useful for storing and separating different gas pairs. As you can see in this animation, the framework breathes, that is, it opens up when a guest molecule approaches it. This breathing allows small molecules like carbon dioxide and methane to enter the pore efficiently. Because the structure is flexible, it can hold more gases compared to the rigid ones. The same breathing helps in separating different gases. Different gases enter the pore to different extent. As you can see in this animation, small molecules indicated by blue balls pass through, while slightly larger ones indicated by red balls gets blocked. This is what makes these useful for smart gas separation of even propane, and carbon dioxide and methane. So, in one material, we get both the functions, high gas storage and precise separation. and this comes truly from their responsive and breathing nature. Now, I would like to highlight a few foundational papers that shaped this entire field. The first paper introduces the permanent porosity inside a coordination polymer, and this laid the scientific foundation for MOF. The next landmark publication established the concept of what we call soft porous MOF crystals, something no one believed earlier. Together, these papers change how we think about solids, not as rigid materials, but as soft, adaptive, and responsive ones. These works by Kitagawa and his collaborators built the entire conceptual framework that the entire next generation of porous material is based on. Now let's sum up why this led to the Nobel Prize. Kitagawa changed how we think about solids. He showed that solids are not always rigid. They can breathe, adapt, respond, and even react. He also discovered dynamic porosity inside crystals. By introducing soft porous MOF crystals, he opened a completely new category of solids. His work also proved that flexibility inside a MOF can create unique functions in sensing, responding, switching, and even storing. And because of this shift from static to dynamic materials, his ideas transformed the future of framework chemistry. Thank you.
Thank you so much, Anisa. Kitagawa showed us that MOFs could be dynamic rather than rigid. Umar M. Yagi took the field from individual discoveries to global system. He asked the question, can we create a mathematical rule book to design any MOF for any specific job? His work led to commercial scalability and first applications such as water harvesting in desert. Our next speaker, Ms. Tanika Chatterjee, will be talking about the work of Umar M. Yagi.
Thank you for inviting me here. Today, we explored the work of a thinker, Professor Umar M. Yagi, who did not merely contribute to the field of chemistry, but fundamentally redefined how matter itself can be designed. While Richard Robson showed the possibility of constructing the metal-organic frameworks, and Susumu Kitagawa went on to depict the flexibility in the soft porous crystals, Professor Umar M. Yagi went further by turning the empirically discovered solids into rationally designed architecture. He turned the porous materials to be built in a rational manner from molecular Lego blocks. These structures were having ultra-high porosity that were permanent even in the absence of gas molecules. The surface area was reported to be higher than those of the conventional porous materials and could be tuned as per the applications that were required at that time. Before deep diving into the scientific contributions by Professor Umar M. Yagi, let us briefly understand his academic journey and professional excellence. Professor Umar M. Yagi earned his bachelor's degree from the State University of New York. He did his PhD from the University of Illinois. Further, he carried out his NSF-funded postdoctoral research at Harvard University. Beyond academia, he ensured that his ideas were translated for modern use. He founded a TOCO and H2 MOF that could help in translating his ideas of reticular chemistry into deployable technologies that could help in environmental remediation in a sustainable manner. Moving further, let us understand how Yagi's contributions eventually led to his achievement of the prestigious Nobel Prize. It all began in the year 1995 when Umar M. Yagi designed his first open 3D MOF. He was inspired from Richard Robson's diamondoid structure, and this design eventually led to the designing of MOF 5 in the year 1999. It was first of its kind as it was highly stable and exceptionally spacious. This designing eventually led to the designing of a rational framework that were termed as isoreticular morphs. These isoreticular morph constructions were done in a rational manner, that is, it was done with a purpose, not discovered randomly. This very idea led to the discovery of reticular chemistry, a new branch that eventually expanded with the designing of ZIFs, that were zeolite imidazolate frameworks and covalent organic frameworks. Many other researchers have significantly then contributed towards the expansion of this field. And from 2014 onwards, Omere Miyagi designed materials that could target of water harvesting that was even possible even at dry arid conditions like those of the desert. From then on, many other researchers have went on to design materials that could target specific applications with a purpose. So, in the year 1999, Professor Omere Miyagi achieved a major breakthrough. He could design MORPH-5 that was a first of its kind. It became a classic example in this field as it was highly spacious and exceptionally stable. To understand how stable it was, when even heated up to 300 degrees Celsius, it remained stable without losing its molecular construction. Here we see the structure of MORPH-5 framework where the yellow spares are actually occupying the cavity of the framework. To further explain how spacious it was, he went on to conduct experiments, and with the help of a nitrogen adsorption isotherm, he estimated that the surface area of MORPH-5 was around 2900 meters square per gram. In simple terms, it meant that if we take a gram of MORPH-5 and let it flat on a surface, it would eventually occupy an area as big as a soccer field. This very idea of designing MORPH-5 eventually led to the tuning of the framework. Here we can see that this is the structure of MORPH-5 where the organic linker was tuned. That is, it was changed. Simply the length of this organic linker changes. That eventually led to the designing of 16 different variants of MORPH-5, both having larger and smaller cavities. This particular idea led to the designing of a new branch of chemistry by Omere Miyagi that he termed as reticular chemistry. Reticular, just like the reticulum, network-like. So he explains in simple terms that reticular chemistry is the chemistry of stitching molecules into frameworks that were in an orderly network-like manner. A similar observation was done when designing of IR MORPH 74 series came into existence. Here also, while he tuned the organic linkers without changing the underlying topology, he saw that on changing the organic linker, it eventually led to the changes in the pore aperture. As he increased the length of the organic linker, it eventually led to an increased pore size, pore volume, and eventually an increased surface area. So, a simple understanding of how MORPH-5 was designed and eventually constructing IR MORPH series led to the MORPH's evolution from a simple microporous material into a mesoporous framework that had larger cavities. Research has been ongoing, and one of the notable examples is that of the NU-110. It was designed at the Northwestern University. This particular material has a record-breaking pore volume and surface area. This meant that this particular material could absorb gas molecules and many other molecules of interest more than those that were reported in the conventional porous materials of that time, like zeolites, carbons, and silicas. Based on this very molecular designing toolkit, many researchers have further expanded this field. They have led to designing of MOFs that could target specific functions and aid in problems around us. Some of the notable examples of these applications are given in this slide, about a few of which I'll explain in the upcoming slides. So, based on the molecular designing toolkit devised by Omari Miyagi, he went on to design MOF 74. This was a basic landmark contribution, not basic, simply a major landmark contribution by Omari Miyagi, since it had high selectivity for carbon dioxide. This particular structure has a striking feature of open metal sites, that is, the metal centers are exposed that are lining the pores. It showed exceptional selectivity and strongly bounded to carbon dioxide even in the presence of gas mixtures. To understand how this very feature was exploited for developing a MOF-based carbon capture system, let us understand this through a simple diagram. Here we see as the emissions of power plants contain carbon dioxide and many other gases, when they are subjected to a MOF-based carbon capturing system, the carbon dioxide gets selectively absorbed while leaving out carbon-free emissions. This very understanding would eventually help in aiding our problems like global warming, as the greenhouse effect can be mediated easily. Once captured, the carbon dioxide can be easily released upon modest heating or pressure changes. Once released, that could be redirected towards utilization by converting them into fuels or chemicals, or for long-term storage by compression or sequestration. So, a MOF-based carbon capturing technology would help us give us a better energy efficient system than those that are reported of traditional liquid amine that really do not show as efficient as a process for carbon capturing. A MOF-based carbon capturing is a greener technology that would ensure to be more energy efficient than the traditional means. Moving further, let us understand how Omari Miyagi turned a mere concept, something that was considered impossible, to a possible reality. How his own childhood experience of scarcity turned into a chemical-driven solution that was quite impossible to be achieved with traditional systems. As a child, Professor Omari Miyagi grew up as a refugee in Jordan. He had to first-hand experience water scarcity and limited resources. This very experience shaped his scientific vision. He went on to design materials that could directly pull out water from air, even at low humidity. Conventionally, the water harvesting systems require the cooling of air below its dew point. This very feature becomes limiting and impractical to be achieved in areas like the arid conditions of deserts. By designing of MOF 801 and MOF 303, Omari Miyagi bypassed this limitation entirely. To simply understand how the MOF-based water harvesting system device works, let us understand it with this simple diagram. Here we see at night, the MOF-based system absorbs water vapor directly from air at the molecular level. During the daytime, under modest heating of sunlight, it releases this water vapor in the form of liquid that could be then redirected for utilizing as a clean drinking water for those in need. This single cycle of adsorption and desorption led to the designing of a monocyclic MOF-based water harvester. Many advancements have been made in this field further, and that has led to the designing of a multicyclic MOF water harvester. Here we see there are multiple cycles of adsorption and desorption taking place to provide with a quantifiable amount of drinking water. So, as a result, we see that a simple idea of how scarcity that was faced by Omari Miyagi as a child shaped his vision to discover something unique, yet addressing problems that need our urgent attention. In this way, reticular chemistry helped turn a concept of material science into true design science. Some of the notable examples of ZIF-8, NU-1501, MIL-101, and many others have been widely recognized for their specific applications that could help create world to be a better place. This very impact was recognized by the Nobel Prize Committee and eventually led to Yagi's achievement of the prestigious award in the year 2025 in the field of chemistry. So, to sum it all up, Omar Yagi helped turn a simple concept into reality, the concept of material science into true design science. Together with Richard Robson, Susumu Kitagawa, Professor Omar Yagi provides researchers with new opportunities for solving problems around us. He inspires us to look closer, design smarter, and find the hidden beauty around us that could eventually change the world for better. Thank you.
Thank you, Chainika. With this, we conclude the segment 1 of Nobel Symposium. I thank all the speakers for insightful discussion and for enhancing our knowledge on the subject. We will begin with session 2, the Nobel Prize in Physiology or Medicine, after a very short tea break. Welcome back. It's time to transition into session 2, the Nobel Prize in Physiology or Medicine. I now hand over the platform to our speaker, Miss Adishri Yadav, and her theme of discussion is immune homeostasis and autoimmunity inside about regulatory T cells.
Hello. So, from FOXP3 to Nobel Prize, a true discovery emerges not from the unchecked ambitions, but from years of scientific inquiry and restraint. A very good afternoon, respected Director Ma'am, honorable dignitaries, and my dear colleagues. Today, I, Adishri Yadav, is honored to present the scientific journey of the guardians of tolerance, the science and success of regulatory T cells. Today, we will revisit the scientific journey from early controversial suppressor T cell concept to identification of FOXP3 gene as a master regulator in peripheral immune tolerance. So, in 2025, the Nobel Prize in Physiology or Medicine is awarded to three remarkable scientists, Dr. Mary E. Branco, Dr. Fred Ramsdell, and Dr. Shimon Sakaguchi. Dr. Mary E. Branco is Senior Program Manager at Institute of Systems Biology, Seattle, USA. Dr. Fred Ramsdell is Scientific Advisor at Sonoma Biotherapeutics, San Francisco, USA. And Dr. Shimon Sakaguchi is Distinguished Professor at Immunology Frontier Research Center, Osaka University, Japan. These Nobel laureates have uncovered the fundamental mechanism of peripheral immune tolerance, especially by explaining that how our immune system protects us from the very destructive attacks. Here is the official press release, which is published on 6 October 2025, entitled Nobel Prize in Physiology or Medicine 2025. The official public announcement was done by Nobel Assembly of Karolinska Institutet, which is awarded jointly to Dr. Mary E. Branco, Dr. Fred Ramsdell, and Dr. Shimon Sakaguchi for their groundbreaking discoveries in concerning peripheral immune tolerance, specifically the identification of FOXP3 gene in the peripheral immune tolerance. Here are the key contributions of our Nobel laureates that leads to the crucial shift from observation to intervention for their discovery in peripheral immune tolerance. In our upcoming slides, our co-presenter will describe it in details. Here, on 10 December, the Nobel Award ceremony was conducted at Stockholm Concert Hall, Sweden. Let's have a brief look.
The first of the three laureates to receive the prize is Dr. Mary Branco, actor at the Institute for Systems Biology in the United States.
Firstly, Dr. Mary E. Branco is awarded with the Nobel Prize.
Family and friends here, and she's followed by Dr. Fred Ramsdell,
Now,
born
award is
in
given to
Elmhurst,
Dr.
United
Fred
States,
Ramsdell.
at the Sonoma Biotherapeutics in the United States. Finally, Professor Shimon Sakaguchi.
Now, Dr. Shimon
Sakaguchi, born
Sakaguchi
in
has been
Nagano,
awarded with the
Japan,
Nobel Prize.
affiliated to the Osaka University in Japan.
So, before going into deep details about their discoveries in T cells, firstly, let's talk about our immune system. Our immune system is a highly adaptive defense network. It identifies the foreign antigens, mounts responses, and clears the pathogen. We often teach immunity as a two-arm system, innate immunity and adaptive immunity. Innate immunity consists of neutrophils, mast cells, dendritic cells, eosinophils, macrophages, and basophils. It is present in an organism by birth, and it provides rapid and broad protection. While as adaptive immunity is acquired by an individual throughout his lifespan, and it provides precise and long-lasting memory response. It mainly consists of T cells and B cells, and together they form a strong immune system. In our today's lecture, we will focus mainly upon T cells and their functions. So, T cells exist in three major functional groups: helper T cells, cytotoxic T cells, and regulatory T cells. Helper T cells contains CD4 plus markers on their surface. It orchestrates the immune response by activating the several cytokines that will activate B cells, macrophages, and other T cells. It recognizes MHC class II bound antigens. The cytotoxic T cells, which contains CD8 plus markers on their surface, it will directly kill infected or cancerous cell by secreting granzyme and perforin. It recognizes MHC class I bound antigens, whereas regulatory T cells, our hero for today, it contains CD4 plus marker as well as CD25 plus markers on their surface, which is used to regulate the FOXP3 gene. It is used to suppress the immune response to prevent the autoimmunity and maintain the self-tolerance. It also recognizes the MHC class II bound antigens. Our main focus for today is regulatory T cells and their functions. But before going there, let's talk about T cells development and their maturation. So, all the T cell development will start to take place in bone marrow as hematopoietic stem cells. Later, it will transform into lymphoid progenitor cells. Later, all the T cell development will start to take place in thymus. These pre-T cells that contains CD3 plus markers on their surface will undergo TCR gene rearrangement and positive and negative selection, which determines antigen specificity. And there, majority of these pre-T cell or naive T cells are self-reactive T cells. And here comes the first checkpoint. These self-reactive T cells have ability to target their own tissues and they may cause autoimmunity. Therefore, our first checkpoint, that is known as central tolerance, is used to remove these kind of T cells through the process of apoptosis, which ensures that only self-reactive T cells are eliminated by the body and the mature T cells will transform into the periphery. So, what happens if some of these self-reactive T cells migrate into the periphery like lymph nodes or spleen? In such cases, when these T cells escapes through the process of central tolerance, this mechanism is then suppressed by the peripheral tolerance, which includes the process of energy and deletion and immune suppression by the regulatory T cell. Here, we can say that central tolerance eliminates the most harmful or dangerous T cells, while as peripheral tolerance controls those who escapes into the bloodstream. Now the question arises that how can we identify the regulatory T cells? What are their cellular subtypes and what is the exact peripheral tolerance mechanism behind it? To unravel this mystery, I may now invite Ms. Sakshi to guide us through the details. Thank you.
Good afternoon, everyone. Very warm welcome to you all. Thank you, Adishri. Wonderful introduction. Today, I will take you all through the journey that led to the discovery of T regulatory cells and immune tolerance. as mentioned by Adishri, this year's Nobel Prize in Physiology or Medicine was awarded to 3 scientists whose work is equally important in understanding peripheral tolerance. Their work reminds us is that science is not always about the answers, but also about courage to question what is not known yet. With this, I will start with the 1995 findings made by Sakaguchi, from where it all began, and the concept of peripheral tolerance started getting attention. But before we dive deep into the T regulatory cell biology, let's take a look at his life and work. Dr. Shimon Sakaguchi was born in Japan in 1951, post-war period. While growing up, he was interested in studying literature, but his father encouraged him to pursue medicine. That led him to join Kyoto University, from where he earned his PhD degree and MD degree. While working as a PhD graduate, he became fascinated by the paradoxical nature of immune system. Normally, the immune system functions to protect the body, but under some circumstances, it shows overreaction and starts attacking the normal cells. Continuing this research, he worked as a postdoc in Stanford and Johns Hopkins University, where he met Professor Neil R. Rose, who is now widely known as the father of autoimmune disease research. There, he worked a paper on organ-specific autoimmune disease in mice. Interestingly, he co-authored that paper with his wife, Noriko Sakaguchi. After finishing his postdoctoral training, he came back to Japan, and there he worked at various well-renowned institutes. Currently, he is a professor at Osaka University. Throughout his scientific career, he has been awarded with so many prestigious awards, including this year's Nobel Prize in Physiology or Medicine, the ultimate recognition one could get in science. In one of his interviews, he mentioned something very interesting. He mentioned that when he started working on these immunosuppressive cells, the research on immunosuppression was not popular. In fact, this topic was often neglected by the academic societies, but he continued his work with passion and perseverance, and with time his discovery got the recognition, and today it has changed the immunology. After all, the Nobel Prize is for the novel ideas, and what he began once was not even considered worthy of research. The major landmark papers which laid the foundation of peripheral tolerance include these 3 papers. Here I'll just mention the key points, and we will discuss these papers in detail in upcoming slides. In 1995, Sakaguchi and his team identified a new subset of T cell which expressed CD25 as their marker molecule and were immunosuppressive in nature. In 1998, his team addressed how these cells suppress other conventional T cells, and how these cells are maintained by the expression levels of IL-2 molecule. In 2003, the genetic regulation of these cells was reported, which was published in paper in Science. The T regulatory cells which we are talking about, so what happens when they become dysregulated? The immune system shifts into us versus them situation. And because of the balance is collapsed, and it results in autoimmune diseases. A very similar idea was described by Paul Ehrlich in early 20th century, where he mentioned that sometimes instead of protecting its own cells, immune system starts showing unusual activities, and he termed it as horror autotoxicus. Currently, the most studied autoimmune diseases include rheumatoid arthritis, multiple sclerosis, and inflammatory bowel diseases. In recent years, the American artist Selena Gomez was diagnosed with lupus, which currently has no cure. And because of it, she had to undergo kidney transplantation. Since then, she has been very vocal about these diseases, and it has brought a critical attention toward these autoimmune research. On the right side, you can see the pictures of children suffering from skin conditions, which arise due to the Treg dysregulated disorders. which includes IPEX syndrome, APCD syndrome, Omen syndrome, and Wiskott-Ulrich syndrome. What I want to highlight here is that the people who suffer through these diseases go through a lot. They just not suffer physically, but also socially and emotionally. And the research focus of Sakaguchi is largely based around these topics. His core areas are autoimmunity and transplantation immunology. He believes Tregs as a link between the genes and the human diseases, and he suggests he thinks that these Tregs could be of therapeutic potential. So while he was working as a postgraduate, at that time he came across a paper which reported that removing thymus from a 3-day-old mice leads to autoimmune inflammation. The inflammation resembled human autoimmune diseases and affected multiple organs. Though it was assumed that removing T cells would result in reduced immune reaction, but what happened? They observed exactly opposite thing. And with that, Sakaguchi became convinced that there are other unknown T cells which are involved in suppressing the activity of self-reactive T cells. But identification of these T cells was very challenging because there was a huge overlap between these unknown immunosuppressive T cells and the other conventional T cells. This led him to ask two key questions, which are there any distinct immunosuppressive T cell population? And if yes, then what contributes to their immunosuppressive function? With that, he began his studies in 90s. Well, at that time, it was already speculated that the CD4 plus T helper cells are the key mediators of autoimmune diseases. But the exact mechanism of immune tolerance and the system which was involved in regulating these self-reactive CD4 plus T cells was not known. And this directly influenced the objective of Sakaguchi, which was to characterize the subpopulation of CD4 plus T cells in their dormant state and to identify a new subset of T cell which was involved in regulating their uncontrolled expansion. Though the research from that time suggested that these CD4 plus T cells, which are self-reactive, are present within the periphery of healthy individual, and their expansion and activation is controlled by certain cell populations which were distinguished by the expression of cell surface marker like CD5 and CD4-5-RBC molecules. But Sakaguchi wanted to narrow it down further with a more specific cell surface marker. And through his flow cytometry experiment, he proposed CD25 as that one defining molecule, as it was the common between these cell population which were high in CD5 and low in CD4-5-RB. And he reported that around 10% of CD4 plus T cells contain CD25 molecules. Now these CD4 plus and CD25 plus T containing cells are popularly known as T regulatory cells. After identifying this new subset of T cell, he then transitioned to study the functional relevance of these T cells in the development and progression of autoimmune diseases. For that, he performed his very popular experiment where he isolated the splenocyte from a healthy mice and then selectively removed the T regulatory cells by employing a specific monoclonal antibody and complement system. Then the remaining T cells that lacked CD25 molecules were then introduced within the athymic nude mice model system, which lacks mature T cell. Within weeks, those mice developed autoimmune diseases and several organs like thyroid, pancreas, and stomach were affected. With that, they established that these CD4 plus T cells, which lack CD25 negative molecules, are the self-reactive T cells, and they might require CD25 plus molecules for maintaining their activity, for keeping them under check. To confirm if it wasn't fluke, he conducted a rescue experiment where he re-inoculated these mice which were containing self-reactive T cells with these T regulatory cells. the disease symptoms were rescued, the autoimmune disease progression was prevented. However, the effect that he observed here was cell specific, because in another set of experiment he introduced the self-reactive containing mice with CD8 plus CD5 plus T cells, and this cell population was unable to suppress the autoimmune diseases. With this experiment he demonstrated that it's the CD4 plus and CD5 plus molecule containing T cells which are involved in maintaining self-tolerance. Furthermore, he also wanted to study if these T regulatory cells have any role to play against foreign triggers. For that, he injected the thymic nude mice with these self-reactive T cells and then challenged those mice with allogenic skin transplantation, or he just immunized those mice with genogenic proteins. What he observed that the mice rejected the skin grafts, and the immune response against those foreign antigens were very strong. However, after the inoculation of these CD4 plus CD5 plus T regulatory cells, the immune responses were normalized against those foreign triggers. Altogether, with these experiments, he established that the T regulatory cells act against both self-antigens and non-self antigens, and altogether they maintain the process of self-tolerance in an antigen non-specific manner. In his previous study, he indicated that when these Tregs become dysfunctional, it leads to autoimmune diseases. He wanted to explore the mechanism of peripheral tolerance in detail, so he conducted the in vitro experiments to study how these T regulatory cells physiologically control the other conventional T cells. For that, he cultured these cells under in vitro condition and subjected them to TCR stimulation. And to his interest, what he found that these T regulatory cells were not proliferating, were not producing IL-2 molecules, but they were unresponsive. He termed that unresponsive state as anergic state. However, despite being anergic, they were highly active as suppressor cells. So when he co-cultured these T regulatory cells with the other conventional T cells, T helper and cytotoxic T cells, he observed that these T regulatory cells were suppressing their proliferation and reduced the IL-2 molecule production. Importantly, what he found that these T regulatory cells require cell-to-cell contact for their functioning, and the antigen concentration which was required to these T regulatory cells was much less as compared to what is needed for the conventional T cells. So, indicating that these T regulatory cells exist in our immune system and they dominate even if they encounter a very small concentration of self-antigen. Crucially, he also found that when these in vitro cultures were supplemented with high doses of IL-2 molecule or other co-stimulatory molecules like anti-CD28, these T regulatory cells started proliferating and they lost their anergic state, and simultaneously their suppressive activity was also gone. However, when these conditions were reversed, the IL-2 molecules were removed, these cells reverted back to their natural state, and with this he demonstrated that these T regulatory cells are naturally anergic and this state is their default state. Finally, with his in vivo experiments, he showed that when these T regulatory cells, which were grown with high levels of IL-2 molecule, were introduced within the athymic nude mice system, it led to the loss of self-tolerance and the autoimmune diseases were developed. In summary, he has shown that these T regulatory cells exist in our immune system in their anergic and suppressive state, and they control the abnormal expansion and proliferation of other self-reactive T cells. With this, I will conclude my presentation. So, the work done by Sakaguchi fundamentally changed how we understand the immune tolerance, and by identifying C2-5 as a defining feature of T regulatory cell, he has demonstrated that these distinct population of CD4 plus T cells controls the other self-reactive T cells and maintain a balance within our immune system. And he has also demonstrated that these IL-2 molecules are essential for controlling the normal functioning of T regulatory cells. The genetic regulation of these cells will be discussed with you all by our next presenter, Priya. And thank you, everyone.
चल रहा है ना? Good afternoon, everyone. Thanks to Sakshi for introducing me. Today, I'm going to present the work of other two scientists, Dr. Mary E. Branco and Dr. Fred Ramsdell, who are going to share the Nobel Prize in Physiology or Medicine this year, along with Dr. Simon Sakaguchi. Here, I will be talking about the scurvy mutation, a small genetic error that unlocked the secret of immune control. It is an honor to introduce these two scientists whose names are now forever linked to one of the most significant medical breakthroughs of our time. Their joint work redefined our understanding of the immune system. Dr. Mary Branco, a molecular biologist and immunologist, started her career from the University of Washington, where she earned her graduation degree in molecular and cellular biology. After that, she continued her doctoral studies, completing her PhD from Princeton University in molecular biology in 1991. Simultaneously, Dr. Fred Ramsdell, an immunologist, established his expertise in West Coast, completing his PhD in microbiology and immunology from the University of California, Los Angeles. So, Dr. Branco and Dr. Ramsdell have the expertise in the area of genetic mapping and translational molecular biology. Their paths converge in the industrial research, where their collaboration began. They worked for a pioneering biotech firm called Celtech Cyroscience in Bothell, Washington. And this company was for the development of pharmaceuticals for autoimmune diseases. At that time, both of them devoted themselves to investigate a profound medical mystery, a severe, rare autoimmune disorder found in a specialized strain of mice called scurvy mice. And their relentless work led to the crowning achievement of their research career, the co-discovery and the identification of the FOXP3 gene. And this discovery explained that how immune system regulates itself, a mechanism known as peripheral immune tolerance. So this is the major article that was published in 2001, where the authors have shown that how they identified the gene FOXP3 and how they characterized it. So moving to the next slide, as I told before, this research journey was started from a mice model called scurvy. And the term scurvy came from a most prominent external sign found in this strain, that is severe skin inflammation. It is a spontaneous mutation and it is a lymphoproliferative disorder. But before this discovery, there were some past studies that already told some features about this model. And those features were, first, that it is an X-linked recessive disorder. Second, it shows lethality within 4 to 6 weeks of age. But the key feature that led to this discovery was that uncontrolled proliferation of CD4 positive and CD8 negative T cell population. Now the question comes that what were unknown at that time. So here the authors have asked some questions, that what is the gene behind this severe disorder and what are the molecular characteristics of it. So let's find out. So in today's time, to map a mouse's entire genome and to find a mutated gene, it is a matter of few days. But in the 1990s, it was like finding a needle in a gigantic haystack. So the journey from a vast uncharacterized genome to a single validated gene, they've broken down this journey into 3 crucial stages. And the first step involves genetic mapping and the recombination frequency calculation. So in this step, the authors have performed a very powerful technique called intersubspecific backcross. So they crossed a mice carrying the scurvy locus with the different subspecies of the laboratory strain to shuffle the genetic deck in the progenies. The logic behind this technique was that to look how some specific markers tend to inherit together with the scurvy trait in the progenies, because in genetics, closely related genes tend to stay together and tend to inherit together
in the further progenies. So from here, this method was incredibly successful, by which they calculated the recombination frequency in between some specific markers and the scurfy locus. So, and they narrowed down their search from a previously known 1.7 centimorgan area to a tiny 0.3 centimorgan distance on the X chromosome that was about 500 kilobase pair long. So moving to the second tool, that was gene identification and the mutation detection. So in this step, the challenge was shifted from the genetic mapping to the physical mapping. And in this step, the authors have constructed sequence-ready back contigs. Back contigs are nothing but bacterial colonies having the fragments of DNA spanning that entire 0.3 centimorgan region. After that, they perform the shotgun sequencing. And when analyzing the sequencing result with the help of BLAST, GenScan-like computational tools, they found 20 putative genes. And they also found a gene that showed strong homology with the fork hat winged helix family of transcription regulators. And they named that gene as FOXP3. But till then, it was not clear which of these 20 genes can be responsible for the scurfy disease in mice. So to identify the mutation, they performed the RT-PCR. After performing the RT-PCR, they sequenced that RT-PCR transcripts from both the normal and the diseased mice. And interestingly, they found 2 base pair nucleotide addition in the coding region of that newly found FOXP3 gene. And none of the 19 genes showed any mutation. They validated this data with the sequencing of genomic DNA from both the normal and the diseased mouse. So from this, they identified the gene and they also have identified the mutation. So this is the main figure of that article that showed that how authors have narrowed down their search from an unrecognized area to a gene, and after that finding the mutation that was disrupting its normal function, that is frame shift mutation. So here, authors felt that only naming the gene FOXP3 and finding its mutation was not enough. They felt for functional validation of it. So to functionally validate their data, they cloned a full-length FOXP3 in a vector and they micro-injected it into the fertilized oocytes of the mice. And that's how they generated the transgenic mice line. And after that, by crossing these transgenic mice with the non-transgenic mice, they monitored the inheritance of the transgene into the male progenies because of their lethality. So they found that the male pups that did not inherit that transgene showed the prominent scurfy phenotype as well as lethality within 4 to 6 weeks of age. But interestingly, the male pups that got the transgene through inheritance, in spite of having the scurfy mutation on their X chromosome, they were completely rescued from the scurfy mutation. They were normal and healthy mice and the survival was good. So from there it was clear that FOXP3 is the gene that is rescuing the scurfy phenotype in this mice model. After that, they performed the tissue distribution studies, and from there they got that spleen and thymus showed the highest FOXP3 expression. Specifically, the T helper 1 and T helper 2 cells showed the highest FOXP3 expression among others. From there, it was clear that FOXP3 is mostly present in cells in the peripheral immune system. So from this discovery, it was clear that FOXP3, mutations in FOXP3 is causing the scurfy disease in mice, and it is related to the peripheral immune tolerance. So the discovery of the FOXP3 in mice immediately opened a crucial question. Did the human equivalent of this gene cause a similar disease? The answer was resounding yes. These 2 articles got published in the same year in 2001, where the authors have studied different human families with a special type of autoimmune disorder. And they demonstrated that in human mutation in human FOXP3 cause a rare but devastating condition in humans that is called IPEX syndrome, immune dysregulation, polyendocrinopathy, enteropathy, X-linked syndrome. So they also have discovered that IPEX syndrome is the precise human equivalent of the scurvy phenotype in mice, creating a severe autoimmune disorder that attacks multiple organs. And these data confirmed the mouse model's remarkable power in science and solidified FOXP3 as a significant component in the immune regulation across mammals. So, after pivotal genetic and physical mapping by Dr. Branco and Dr. Ramsdell, the world knew that mutations in FOXP3 is causing the scurvy disease in mice as well as IPEX syndrome in humans. But the final elegant piece of puzzle, the ultimate functional clarity, came from the laboratory of Dr. Simon Sakaguchi in 2003, when Dr. Sakaguchi asked a question: is it FOXP3 regulating the function of Tregs? So Dr. Sakaguchi's team have provided the definitive proof. Pointing. Sorry. So Dr. Sakaguchi's team have provided the definitive proof that FOXP3 is not just a gene in a pathway. It is the master regulator for regulatory T cells as well as the lineage-defining transcription factor for the development of regulatory T cells. In the image, as you can see, when FOXP3 is present, the disease phenotype of colitis as well as gastritis in colon as well as in stomach is gone, but the disease phenotype is prominent when FOXP3 is mutated or absent. Their laboratory have also shown that FOXP3 expression is mostly in cells with CD4 positive and CD25 positive T cell population. So these landmark 2003 finding ultimately completed the picture started by the scurvy mice and also established FOXP3 Treg axis as a single most mechanism in maintaining self-tolerance and preventing autoimmune diseases. So now finally the question is solved, that what is the master regulator behind the development of T regulatory cells? It is FOXP3, and these landmark research work of these three scientists finally led to the most prestigious award in the area of science, that is Nobel Prize in 2025. So now I will conclude my part. Now I will call Adhishri to discuss with you the role of regulatory T cells, its clinical impact, and the future directions. Thank you so much.
So now, let's talk about the clinical impact, that how the decades of discoveries have translated into the real therapeutics by taking a journey from mechanism to medicine. As we all know, when immune tolerance fails and the Treg imbalance will occur, therefore it may lead to disease progression. Here we have two scenarios: when Treg activity is increased and another when the Treg activity is decreased, and interestingly both may lead to the disease progression. For examples, in case of cancer we have high Treg activity and it may lead to the suppression of anti-tumor immunity as well as cancer invasion. It may also lead to some of the chronic infection, while in other scenarios where the Treg activity is low, like in autoimmune disorders, metabolic disorders, cardiovascular disorders, neurodegenerative disease, and graft versus host disease, here we have low Treg activity. In autoimmune disorders, the low Treg activity leads to systemic lupus, multiple sclerosis, and rheumatoid arthritis, while in metabolic disorders it leads to type 2 diabetes and NAFLD. In cardiovascular disorders, it may lead to myocardial infarction and atherosclerosis, while in neurodegenerative disease, it may lead to Alzheimer's, Parkinson's, amyotrophic lateral sclerosis, while in GVHD, it may lead to the transplantation. So here we can say that when the Treg activity is high, Treg depleting therapies are given, and when Treg activity is low, Treg enhancing therapies are given. So to correct this imbalanced Treg activity, we have multiple therapeutic strategies. As we know that our Nobel laureates have identified several markers like CD25, CTLA4 and FOXP3. So let's see that how their presence or implications have been applied in modern therapeutics. In case of Treg depletion or inhibition therapies, which is given in cancer or various chronic infection, we have surface markers targeted therapies and intracellular markers targeted therapies. In surface marker target therapies, the target markers is used are CD25 as well as CTLA4. It is basically monoclonal antibody based approach or drug conjugates. The drugs which are used are basiliximab and ipilimumab, which is now FDA approved. In intracellular markers targeted therapies, we have FOXP3 target marker. It is basically antisense oligonucleotide approach, and the drugs which are used are AZD and HDAC inhibitors, which are under phase 1 clinical trial. Now, here are some Treg enhancement or expansion therapies which are given in autoimmunity, allergy and transplant tolerance. Here we also have cytokines and co-stimulatory molecules as well as cell-based therapies. In cytokines and co-stimulatory molecules, the target pathway is IL-2 based and CD25. It is basically a modified protein, and the drugs which are used are aldesleukin and abatacept, which are FDA approved. And the cell-based therapies, which are very common nowadays, are non-engineered Treg infusion and CAR T cell therapies. The target marker which are used are CD25, FOXP3 and also engineered FOXP3, and it is administered in the patient suffering from GVHD and type 1 diabetes. So behind these classical markers, that is CD25, CTLA4 and FOXP3, there are also several Treg based markers which are now being actively explored, and they have been identified from last 2 decades. Here are also some cell therapies that is enhancing the Treg functions, which is used in autoimmune disorders, transplant tolerance and chronic neuroinflammation. And one such disease that is under phase 3 clinical trial is ORCA-T, and it is administered in the patient suffering from acute myeloid leukemia, myelodysplastic syndromes. These are basically T lymphocyte replacement, or also known as adoptive transfer Treg therapy. Here are some drugs that is depleting the Treg function, and it is administered in various types of cancers. One such drug that is marketed and under phase 4 clinical trial is ipilimumab, commonly known as Yervoy, and it is administered in the patient suffering from melanoma and renal cancers. It is basically used to block the CTLA4, which activates the effector T cell, and it leads to the Treg depletion in humans. So till now we have known that how Tregs are being identified, what are their functions, and got to know about their clinical importance. So now let's summarize its journey of 5 decades of discovery from suppressor concept of master regulator in peripheral tolerance. In 1970s, the Richard K. Gershon discovers the suppressor T cell theory. In 1995, Dr. Sakaguchi's proposed the suppressor T cell with CD25 plus marker. Later, in 2001, the human Tregs were first characterized with CD4 plus as well as CD25 plus marker. And later, in 2003, Dr. Mary E. Branco and Dr. Fred Ramsdell proposed the FOXP3 was identified as lineage defining the transcription factor for the Tregs, and all of this work will lead to the Nobel Prize in Physiology or Medicine in 2025. Therefore, we can say that Treg science is not a journey that has been stopped, it is still continuing. In India also, there are many institutions which are actively working on Treg cells, that are IIT Bombay, Tata Memorial Center Mumbai, AIIMS New Delhi, NII New Delhi, JNCASR, and NCCS Pune. And here is India's first CAR T cell therapy, named as NextCAR 19. It is the first indigenous humanized CAR T cell therapy that is represented as living drug of India. It is developed in collaboration with ImmunoAct IIT Bombay and TMC Mumbai. And it is administered in the patients suffering from multiple myeloma, B-cell lymphoma, and glioblastoma. And this innovation is supported by DBT and BIRAC. It is also presented by our Prime Minister Narendra Modi during ESTIC Conclave, New Delhi, India. Thank you so much.
With this, we conclude this session. I thank all the speakers, Adishri, Priya, and Sakshi, for a very insightful presentation. To share some final thoughts and conclude this session, may I request Director Ma'am, Dr. Radha Rangarajan, please join us on stage.
I think we can all agree that the students did a fabulous job today. Let's give them a big round of applause. It was a real treat to learn about areas of science that may not be of immediate interest or of immediate research in CDRI, but where there is growing interest in the rest of the world. It gives us inspiration to look at such research more closely for our own purposes, even and for application. So I'm really very impressed that the students put so much thought and effort into presenting a coherent story and explaining to us from the basics all the way to advanced applications. This shows to me that even if there is a very complex story to tell, our students have the ability to read, to understand, to assimilate, and then to communicate. These are great skills to have. These are important skills to learn during the course of a PhD. And I think the more we see of this, the more we are assured that our PhD program is actually delivering what it should be. Congratulations to all of you. May I ask the students to come up on stage? Now, in the past, we've really not done too much Q&A, but although I didn't tell them to be prepared for it, maybe we can do a little bit of a Q&A, and it can be more of a discussion if you wish. Come. All of us can talk about it because this is, maybe you had some thoughts and maybe you want to explore something. Maybe they can share their views. Anyone has any questions? Okay, I will ask you something maybe to think about. Do you think that we can use metal organic frameworks for drug delivery, where perhaps we can look at specific applications? Are there specific niches in the body where these metal organic frameworks with drugs in them can be used? Because you talked about activation of these metal organic frameworks, right? So are there specific niches in the body where they might be activated so we can look at applications of that nature? Microphone? You can come to this stage. Yeah.
So as ma'am asked, yes, definitely we can use, because recently there is a MOF with zirconium based and it is used for a tumor therapy by dual attack method. So if ma'am allow, we can have a new project of MOF in CDRI and we definitely can work on more for drug delivery applications.
Good.
Thank you.
Thank you. Tejinder, do you want to add anything? What kind of what makes these morphs activated to deliver their cargo? Because you need to load them and then you need to unload them in the right places to make them effective delivery systems.
Yes, ma'am. Many morphs they are being used for targeting delivery, which are deliver the drug based on the need and based on the environmental changes like pH responsive morphs are available. Some have been already tested in preclinical, some are already in the phase 1 and phase 2, where people are studying it for drug delivery purposes with at the site, at the need, and based on the environment.
Great. And are there scalability challenges?
No, morphs are easy to scale.
Yeah.
They're much easier to make. Problems comes in the loading and unloading. When we really want to, there are some challenges which need to be tested because these morphs, you see, there are a variety of morphs. Many same morphs are being used for very different applications. But when we want to use particularly for drug delivery application, we need to make them stimuli responsive. So adding some features which can deliver drug as per the need or as per our requirement.
Great, thank you. So pharmaceutics and chemistry can look at some of these applications. Targeted drug delivery is an area of great interest because you could cut down on adverse effects if the drug is delivered to the right place. Any questions for the biology team? Yeah, Anil. Oh, another one for chemistry. Okay.
So carbon nanotubes are very well known for delivering drugs at particular location. Only thing is that the clearance and toxicity things like in the human body or clearance of these nanotubes once the things are done. So do you have any thoughts on this, the metabolism part of MOFs if you have come across anything?
Does anyone here have any opinion on that? Okay, maybe it's... Does anybody in the audience know? You want to answer, Tejinder? Anything about metabolism of these morphs versus carbon tubes?
Related to carbon nanotubes, they are not morphs. They are basically carbon materials. They have issues with the problem with if you want to deliver the way of delivery, how you can use it. But as per morphs are concerned, there are some issues like toxicity issues because we are going to use metals. These are metal organic frameworks, and not all metals are suitable for drug delivery application because we want to take it inside the body, and that these are carriers and they are in having a large amount of metals. So this is the basic concern. Of course, but people are thinking of metals which are biocompatible, and thus those morphs are also being studied heavily for drug delivery purposes.
Yeah. So difference between carbon nanotubes and morphs is the three-dimensionality and how you can pack things in. So, okay. Are there additional questions? Yeah, sorry.
Yeah, just maybe I missed it. So is there anything is known how the drugs are released from this morph when they are entered in the cell?
I think sort of Tejinder tried to answer that by talking about where they get activated. And that's a critical part of this whole construct, that you load them, but then you want to release them in the right place and they have to be activated there. And there's some niches where this can happen, right?
So
can you tune that aspect? You can. pH responsive or? I see. Okay, so detection of specific markers or antigen or pH. These are some of the triggers that can... Okay, very good. Any questions on the regulatory T cells? Any applications that were triggered in your mind by the presentation on the regulatory T cells? Questions? No? Okay, Anil, you have a question?
So I don't have any question, but I have just regulation part of it. Like there are two things. You spoke about CD25 surface expression and FOXP3 intracellular expression. How do both of them correlate each other? So how the relationship between this CD25 and FOXP3 is there? Second thing is, are there any small molecules like as far as I know, that there is something called BCP, which can proliferate T regulatory cells within the in vivo experiments. People have shown beta karyophylline करके एक compound है which can proliferate. So, are there any small molecule regulators apart from this antibody-based mechanisms or genetic mechanisms? Are there any small molecule things to make the balance? So, if you have come across anything, something like that.
The pipeline that you showed of products in clinical development, they were mostly biologicals, right? There were no small molecules in that list.
Basically antibody and drug conjugates, as well as there are adoptive Treg based
Right.
therapies which are commonly used, and for
That
and
requires
there is also
what?
CAR T cell therapies. These are modified version of CAR T
Yeah.
cell
So
receptors.
small molecules, not really.
There are not
Anything on to add, Neeraj? I don't know about small molecules in this space.
So basically, like your first question was like whether the CD25 and FOXP3 have some relation actually. So the thing is like FOXP3 is the master regulator, and ultimately when it basically get activated through the SMAD pathway or basically like JAK-STAT pathway like that way. So it basically like activate like many genes. Those are required for the regulatory T cell specific marker expression actually. Like. So this is the one thing. CD25 is the
My question still remains the same.
yeah.
CD25 quantitative intracellular expression will have any impact on the CD, like the FOXP3 quantitative intracellular expression will have any impact on the CD25 surface expression?
No, that's not the case actually. So CD25 is the specific marker for the Treg cells. But basically,
So they are the two expressions
yeah.
would be correlated.
Yes. And then second thing, FOXP3 is also expressed on the Treg cells. So both of them specifically express the Treg cells only actually. So that's the main specific correlation they have. Right now, there are some therapy, for example, like IL-2 based therapy. When you give like a small IL-2 based conjugate and then some kind of mutant to the patient, the small quantity of IL-2 itself is basically get help to them these Treg cells to get activated actually. Under the case of like autoimmune disease and multiple neurodegenerative disease and many things actually. And in terms of therapy, in case of like other autoimmune disease, we have like specifically cell-based therapy. Currently, they are majority of them are the phase 1, 2, 3 clinical trials. We have like the antigen specific Treg cells development also, where like you don't have to like you don't have to basically tackle like the non-specific like Tregs basically non-specific manner. They basically like antigen specific manner you can deplete the activity of the effector T cells like that way. So these are the things basically undergoing development. Yeah.
And Neeraj, how does one achieve a balance in these therapeutic modalities? Obviously, too much of the Treg would be counterproductive because then there may be then patients would be susceptible to infections.
That is true, ma'am. Actually, like if you have like too much Treg, if the patient is basically having certain infections, so the immune cells may not be like having productive nature because like Treg cells, they basically target like the effector T cells in a non-antigen specific manner. Actually, like
right.
They're the things that yeah.
Okay. All right, thank you very much. Students, you did a fantastic job. We're really, really proud of what you've done today. I request the mentors to come up on stage as well. A big round of applause to them. We wouldn't be here today without the two of them really mentoring the students. And thanks to all of you for supporting this effort and for being here in large numbers. This is a very important platform through which our students gain confidence in being able to present and being able to tell a complex scientific story. And I really appreciate the fact that you took time off to join us. Sarah, would you like to? So now I hand it back to you to conclude the event.
It's time to felicitate our mentors and appreciate their efforts. Ma'am, may I request you to honor our mentors, Dr. Tejinder Thakur and Dr. Neeraj Jain. Please give a big round of applause to them. Now it's time to felicitate our speakers. First of all, from session 1, Ms. Ipsha Shruti, please come up on the stage. Next, it's Ms. Anisa Noor. Ms. Chanika Chatterjee. Now our speakers from session 2, the Nobel Prize in Physiology or Medicine. First of all, it's Ms. Adishri Yadav. Ms. Sakshi Yadav. And Ms. Priya Saha.
Now I request our moderator, Ms. Sara Fatima, to kindly accept the felicitation. Thank you.
We get a picture with everyone. I request everyone for a group photograph to come up on the stage. As we conclude this successful event, I have the privilege of proposing the vote of thanks to acknowledge those who have made this gathering possible. First and foremost, I would like to express our deepest gratitude to our director, Dr. Radha Rangarajan, for your visionary leadership and for providing the platform and resources necessary to bring this event to life. We also owe a great depth of gratitude to our mentors, Dr. Tejendra Thakur and Dr. Neeraj Jain, for your patient guidance, your technical oversight, and for sharing your wisdom behind the scenes. A special thanks goes to our speakers, Ipsha, Aniza, Chanika, Adishri, Sakshi, and Priya. Your thought provoking presentation have truly enriched our understanding and knowledge on the subject. I want to extend a huge thank you to our helping staff, including the technical team, the catering crew, and the maintenance staff. Finally, I would like to thank you for your presence. Have a wonderful day.